chapter 2, vectors. This is another chapter that we're gonna brief you about how to prepare yourself for the whole topic of the classical mechanics. Most of the physics phenomenon or quantities that you measure, mostly they are vectors. So you will learn how to use the vector operation, and after this we will learn more about physics using vector as a tool. Let's start with this. To understand about the vectors or the property of vectors, you have to know about two different quantities. So first one we call scalar, and the second one, what we're going to learn today, is about vectors. What is the scalar? So scalar is the quantity that you require only magnitude and you can complete it. So no direction. So this is the mistaking. So make sure you understand and cross this off. But what is vector? Whether you for vector you require magnitude and also the direction. For the completeness, to explain about the quantities. So what are scalar? So for example, the position. If you represent one objective or one object that lay down in space, you can represent x, y, and z as a coordinate at some position, right? When it's moved along the x-axis, the position change from one position to another position. This is what you represent it. So position, just the point, and location. So position is the same meaning as a location, right? Not only the position, when you have moved through the position, or when you are moving through the part. So this calls the distance. Distance is the total path that you move from point A to point B. So in this case, like if you're moving from A to B, I rather remove this first. So when you start moving from point A to point B and you create the path, the total path is the distance. So you have to count as a total, right? You will see how distance different from the displacement later. And how about the speed? So if you know the total distance that this part moving, right, and you divide by the time that has been taken along this part, like the t is the time that you moving from point A randomly to point B. So this is what you got, the speed, the distance over time change. So these are examples of the scale quantities. Not only this one, you also know mass, right? If you would like to quantify the objects and try to measure the properties, one of the things that you learn from the first chapter is the mass. You know the dimension of mass is big M, and the unit is in kilogram with SI unit system. Not only the mass, but also, for example, like temperature, also the scalar quantity as well. So how about vectors? Vector, you require both magnitude and direction. One of the example is displacement. So when you claim about the distance is the total part that you moving from point A to point B, right? But if you count only from the initial point to the final point, the shortest distance, the black arrow represent shortest distance. We call this as a displacement, right? So not only you have a distance for the shortest distance for displacement, you also have the direction that displacement point to. So you require magnitude and direction to complete the definition of the vectors. So the displacement is the shortest distance from point A to point B to some specific part and with some direction. So we represent delta R or delta X in one dimension for the displacement. If you have a displacement, divide by time, so you have the definition of the velocities. Velocity is different from speed, since the speed is the distance over time, but velocity is displacement, so this one is displacement over the time. So what is the velocity here? If you see from this figure B, you see this spark moving at one time point, the position is here, and another time point the position is here. So the difference of the position, difference of the displacement, you got the delta S. Delta S here is the displacement from two different points. So with this over t, you got the velocities. And how about the acceleration? Acceleration is the change of the velocity over the times. So when you have the direction of the velocity change, or you have the magnitude of the velocity change, you can find the acceleration. So it's increase or decrease in terms of the velocities in time. So these are difference between, this is the difference between the scalar and vector quantities. To get into inside information of the vector, you have to know the basic quantity, as I said. So you have to find the property of the magnitude, and another thing is the direction. So magnitude is, if you have the arrow pointing like this and you represent, this is the vector A, right? How you can find the magnitude from the graphical figure. So it's supposed to be the length of this vector. For example, like this, if you count 1, 2, 3, 4, 5, 6, 7. So this vector A, to writing as a vector, you need the arrow size on top of the alphabet, I think that you're gonna call it as a vector. Or if you see the bold one, so here this A can represent the vector A if you find in the textbook. So what is the magnitude of A? The magnitude of A represent like this. You can count the length of it. So in this case it's 7 units. So 7 units is the magnitude of this vector A. And what about the direction? Mostly if we would like to identify the direction, we can use compass. The compass for identify like north, south, east, west, right? For this direction, you can see it's like pointing to the northeast direction. But the direction here is not quite precise, because if you would like to quantify or measure some things like physical properties, you need to identify it precisely. In this case, we use the angle to represent the direction. So you can have the angle from x-axis or horizontal axis, or it can be from the vertical axis. It depends on your definition. For in this case, I define the direction from the theta. Theta is from the horizontal x-axis. So this is what I define. This is the from. If you know the trigonometric conversion, so now you can use the relation of the right angle triangle, right? And you know the theta, and this if A, B, and C for continuous, you can use like sine theta, cos theta, and tan theta to use to represent the direction of it, right? Sine theta is B over C here, and cos theta is A over C, and tan theta is B over A. If this is the right angle triangle, so I'll write it like this, right? So now you know two properties that required for the vectors: the magnitude and the direction. There's another way to explain about the vector properties as well. If you can identify the vector both are like perfectly similar. So if they are in similarities, that you mean you have to have the magnitude of A equal to the magnitude of B, and also the direction as well. Theta here also the same as the theta here. So this is the definition of the perfect equalities. And how about another properties? You can switch whether you have A plus B or B plus A. They're both the same here, right? So this is an example. So if you have the blue arrow represent vector A, and you have the orange represent B. So the red one is the sum of this arrow. The way to sum, you can use the end and the head of the arrows to connect with another end and the head. And finally, you pointing the resultant of the vector from the end to the head. So the A represent A plus B. Rather than you have A and then B, you can change to B plus A. So when you point from the end to the head and another end to the head, and when you try to find the resultant one, the B plus A is exactly the same as the A plus B, right? The magnitude is the same, and the theta or the direction is the same. This is the properties of the vectors. Not only from these two vectors, another property is their own minus, or you can do self, like if you have A identically and you subtract themselves each other, this vector can go to zeros. For example, if you have the A one as a blue line, if you multiply minus 1 to A, this means you still have the same magnitude of this vector, but you flip the direction. So rather than pointing to upward like this, it's reversed to another direction. This is how you multiply with the minus sign in front of the vectors. So you change the direction of that vectors. However, when you do sum it up, when you start with these blue arrows and it's go back with the minus 1, it's exactly like mean you stayed at the same position. So the resultant of these vectors is zeros. I mean like you walk forward and walk backward. So finally you still at the same position. So this is the identical vector that minus each other. How about the other ones? Another one is you can do commutative. So rather than you group up with the first like A and B and plus C, you can A and plus and group up B and C. What is happening graphically? So if you represent the blue one as the A, and orange one as a B, and green one as a C, what you see here, the red line is the resultant between B and C. Right? This means you group up B and C first, and then you plus with A. So A plus B and C, you got the gray one as A plus B plus C. So what happened here? Rather than you group B and C first, now you group A and B first. You see the resultant of the addition of A and B. So you get the red one is A plus B vector. Yeah, right. We did tell you about head and tail connection to get the resultant vector. So now you got A at the initial point to the end of the B. So this vector is A plus B. And after that you plus with C. So this is the result of the A plus B and then plus C. So you can see the gray arrow here, they are exactly the same. So this is the another properties of the vectors. So how about the subtraction and the multiplication with the scalar constant? So if you have the vector A as the blue line here, blue arrow here, and you have the orange line for the B, if you would like to do A subtract with B, the resultant of the vector A subtract B is these green arrows. So you can see the head of the arrow point to the initial vectors, and the end is from the later one, which is B. So how can you explain about this? If you know about the plus way of the vector, right, the A is still the same direction, but if you minus B, initially B is pointing to this upward direction, this is B, right? If you multiply with minus 1, you inverse the direction, right? Direction point inversely, right? Okay. But the magnitude is still the same. It's still parallel, but point to different direction. So now you have this as a minus B vector, and then you can sum it up. So you have n to head and n to head, and this is another vector is called A plus minus B, and you can see these green arrows are exactly the same. So the way to do a subtraction in vector is like you have vector A plus with minus B vector. It's not zeros in this case, so sorry for this. This is some mistaken. It can be 0 if A equal to B, right? But this case is not 0. And how about another property is if you would like to multiply with M or multiply by M. So if you do this, initially if vector A have its own magnitude, when you do multiply with M, so what you change the magnitude of this vector. Here, for example, maybe I'll rewrite it again. Like this, for example. So what is the magnitude of A initially? So you can count 1, 2, 3. So this is 3 units in vector A. Direction, okay, it's still theta here, it's as a direction. But if you have M multiply with A, so what is supposed to be? Like 1, 2, 3, 4, 5, 6, 7, 8, and 9 here, right? Here, so if you count, the magnitude is like 9 units. So what M is supposed to be in this case? So M is the factor, so it's supposed to be 3, right? If you have 3 multiplied by 3 is 9. So M is like you change the magnitude of initial vector, but what happened to the direction of vector MA is still pointing to the same direction as A. So M is changing the magnitude of that vector, but the direction is still the same. Not only that, properties of vector that help you to do the vector operation after this, you have to understand about the coordinate or the components of the vectors. And we use, like most of the time, not only in the Cartesian coordinate, we also use the polar coordinate as well. How different of these two coordinates? So you may get used to the Cartesian coordinate because the x, y, and z position that you always claim about it. So this happen on the x and y and z axis, but in this case I will write into the first. If you have one vector, you know that this vector combined with two different sides. It's from rectangle rule, right? This is like Pythagoras. Because from the right angle, you know, the two different sides to combine as this the longest part that opposite to the rectangle. So from this, you know, if you would like to find this C from A and B, these sides I can rewrite it. So rather than call A, I call this as AX. It's components of vector A in X direction. And I call this component as AY, the components of this vector A in Y axis. And why it look like this is because when you have the vector point out this direction, if you would like to break for the components, the easiest way to remember or to use it is if it's close to the angle, you get this as a cos theta. And if it's further away from the angle, you got it like a sine theta. What is the reason of it? It's because it's represent like the circle and the way that angle form. Like if you have the cos zeros, which is you count 0 here, is equal to 1. Right? If it's sine 90 degrees, for example, I'll write that here. Because you claim this as an angle, right? For this position, is when theta is 0, so cos 0 is 1. So at this point, you get the value of it. But how about this? If theta is 90 degrees, you got sine 90. So sine 90 is also 1. You got the value of the A in the Y direction. So this is how you claim that, like when you get close to the angle, you get cos theta, and if it's further away from the angle, you got sine theta. Right? For shorten, when you solve this and you like to break a component, let's look after the angle first. And if you have this vector and would like to break a component, so you got A cos theta in the close theta components, and further away is A sine theta. This is one. But how about the component in polar coordinate? So rather than you have x, y, you can claim another coordinate, like you got r axis and you got theta axis. That's how you point out this position out of r and theta. So you can represent this point from r and theta as well. If you would like to break component of r, it's exactly the same, right? The cross to angle is r cos theta, and further away is r sine theta, where r is the magnitude of vector r, or that part is vector a if they are exactly the same. If you like to find the magnitude of that vector, you can have the component on each part, like ax component square plus ay component square. Since cos square theta plus sine square theta is equal to 1, so you will have a afterward. And how about tan theta? You can use theta to represent the direction, right? This is the direction, and this is the magnitude. So for represent the angle or the theta, tan theta is the height, right, which is ay here, and this is the ax. So you have the ratio between ay and x to find the tan theta. So these are the coordinate and the representation. Not only that, you can convert from polar and to Cartesian coordinate, or you can convert from Cartesian to polar coordinate. The polar is theta, r, and theta, right? So if you know the theta and you know the r and theta, and then now you can know x and y from this relation. And this case, you know already, like x here is when you break a component cos theta, and when it get further, which is on this side, is r sine theta. This is how you convert it. And if you like to convert from the Cartesian to polar, you also know the theta, right? And from the right angle triangle here, y over x is the tan theta here, right? And the magnitude of the vector r here is the components of it, like x squared plus y squared, as shown here. R is called hypotenuse, which is the longest distance opposite to the right angle. And this theta now represents the counterclockwise direction, so here is this direction.